So the third talk in this session is by Stephen Catterall from BioSS, and he's going to talk to us about modelling disease spread when there is limited data on the distribution of the host. Over to you, Stephen.
Okay. Right. So yeah, I'm just here to say a bit about EPIC's work on modelling spread of disease when the distribution of the host is unknown or there's uncertainty. So I was claiming that modelling the sort of spatial spread of animal disease is something that is useful. We can understand observed apparent patterns of spread of a disease in an outbreak setting. And we can also use modelling to explore the implications of potential sort of disease control measures. But the thing about modelling is it usually requires data. So ideally, we would like data on the spatial distribution of the disease host, and also data on the disease itself. This might be from, say, sort of reported cases of the disease with associated times and locations. So if any of these data sources are not available or are sort of poor, then that kind of makes the modelling of the spread more difficult. So just giving an example to show you what I mean. There's this. These are sort of 3 maps showing the spread of African swine fever in wild boar in Estonia. This was during an outbreak that happened a few years ago. So you can see in the middle map there are some kind of blank regions of Estonia where there are no cases, and you might think, well, is that because of a lack of hosts in those blank regions, or is it simply that the sort of disease hasn't actually arrived in those regions yet? So, yeah, if you don't know the distribution of the host, it complicates the interpretation of the disease case data. But conversely, in the absence of the sort of knowledge of the host, these disease cases do tell us something not only about the disease, but also about the distribution of the host. And there is often uncertainty in our knowledge of the host distribution, which is unfortunate given that most modelling approaches do require knowledge of the sort of host spatial distribution. So data may simply not exist in some settings, particularly with the case of wildlife. On the other hand, data may not be publicly available. That might be the case for sort of livestock in farms in some countries. So a general kind of strategy to handle this sort of lack of data on the host distribution is to basically make use of data that are actually available. So we can make use of sort of land use data and climate data for the region of interest, anything that might help to explain the sort of variations in the sort of host density across the region. So rather than this, what I call a sort of standard modelling approach on the left, where you have a sort of data on the distribution of the host that feeds into a kind of spatial spread model. On the right, there's a kind of alternative approach whereby there's a kind of model for the population at risk, which feeds into the spatial spread model. And that model for the population at risk is informed by these spatial covariates, such as land use. So this is a general strategy that has been explored by others in the epidemic modelling literature. So Mike Tilsley and others at the University of Warwick have explored some aspects of this approach by looking at models for the distribution of farms in the UK and USA using using sort of land use data. So I've just taken this, this is illustrating different models for the distribution of farms in the county of Cumbria. You can basically have different levels of granularity in the sort of land use data that you're using, and you can also make different assumptions about which categories of land use correspond to sort of farms. So this work was motivated by some of these sort of privacy issues in the context of the USA. So in EPIC, we've developed this IPAR approach, which stands for Inference of Population at Risk, which integrates this kind of model for the host distribution informed by sort of land use and other covariates, and that's integrated with a kind of model for the spatial spread of the disease. So we can sort of take into account any prior knowledge we have of the host distribution, and the sort of disease case data are assumed to inform not only the sort of spatial spread model, but also the sort of model distribution of the host. So this entire model is then sort of fitted in a sort of Bayesian framework to the available sort of cases of the disease. So this is just a kind of illustrative example going back to wild boar in Estonia and ASF. So we can combining the sort of case data on the left with sort of Korean land use data in the middle, which is assumed to explain some of the sort of variation in the host distribution across Estonia, and then you can combine those to give model some of the outputs of the model on the right. So there's kind of estimated effective susceptibility across Estonia, that's one component of the model for the sort of host distribution, and also you can create risk maps showing sort of predictions of future spread conditional on sort of case data up to a certain time in the outbreak. In summary, I'd say that modelling disease spread can be challenging when there's uncertainty about the sort of host distribution, but our strategy is generally to make the best use of the data that are available, and we believe that this IPAR approach can help to sort of fill a gap in the sort of disease modelling approaches, so that ultimately we're kind of best prepared for any sort of future disease outbreaks, such as when ASF arrives in the UK at some point. There's more details I've got a poster out there and also a preprint. So yes, thank you. Yeah.